I will be talking about design of piezoelectric materials for high temperature applications. As you know, during the last several years, there was a very impressive achievements in the, among the piezoelectric materials. The piezoelectric properties increased greatly, and mostly it is related to the invention of relaxer-based single crystals. But what is wrong with these crystals, what is not good? First, they are crystals, thus they're expensive, hard to prepare, and the same compositions in ceramic states usually have much lower piezoelectric properties. The other problem is that they work at low temperatures because Curie temperature is comparatively low, and what is more important, they have morphotropic phase boundary, and the phase transition between two phases at a temperature lower than Curie temperature. And of course, if you have phase transition, the main structure changes, and it is impossible to heat the crystal above this depolarization temperature. And one more problem is that the KRC field is comparatively low, 2-3 kilovolt per centimeter typically, which make the material not very stable, especially at elevated temperatures. But high temperature materials are needed, and here we show the review of existing materials, which piezoelectric materials, ceramics, which can work at high temperatures. And you can see that the higher the okay. Okay, you can see that the higher the temperature, the lower the working temperature, the lower the piezoelectric coefficient. I'd like to report the development of new morphotropic phase boundary ceramics, which has very large D33, effective D33 coefficients, 2500, and it is observed at 200 Celsius, and you can see that this is much larger than the in existing materials. It is the composition based on the known solid solutions, what is new is the addition of lead tin niobate, several percent, but this several percent make difference. First, I report the properties, and then I try to explain the mechanisms behind this behavior. You can see that X-ray diffraction shows the morphotropic phase boundary when concentration of lead changes. We observe the transition from at room temperature from rhombohedral to tetragonal phase, and temperature dependence of permittivity shows the Curie temperature about 400 Celsius. This is comparatively high. And at lower temperature, you can see this anomaly, which is associated with the phase transition between rhombohedral and tetragonal phases. This is transition related to morphotropic phase boundary. This means that the boundary is inclined in the phase diagram, and upon heating, we can obtain the phase transition. And these are the properties at room temperature. You can see increase of spontaneous of remnant polarization as expected at morphotropic phase boundary, and quite high KRC field. This is about order of magnitude larger than in relaxer-based crystals. Then, if we measure small signal piezoelectric coefficient, we again see the maximum of this coefficient and electromechanical coupling factor at morphotropic phase boundary, and the value is about almost 600. This is high value, but you can say that it is not very high. Some ceramics have larger values, but you need to remember that in that ceramics, the Curie temperature is low. We are talking about the materials with high Curie temperature. And if we measure the strain under unipolar electric field, we observe almost linear dependence of strain on electric field with small, comparatively small hysteresis. This means that effective piezoelectric coefficient, which is measured as the relation between strain divided by field, is about the same as small signal coefficient, a little bit higher, and depends on depends on field. But now, if we compare different ceramics designed for high temperature applications with high Curie temperature, we can see that our ceramics is the best one. D33 is higher than for the existing ones, and effective D33 is much higher. This is good, but this is not the whole story. It is not enough to have high Curie temperature. We need to be sure that the material can still work at high temperatures. Thus, here, the dependence of properties, piezoelectric properties, on the temperature at which the material was heated is shown. Thus, the material was heated up to these temperatures, then cooled down, and properties are measured. And we can see that it is quite stable up to 250, 350 Celsius. We observe no change of properties. Thus, this is good material for applications. For some materials, the properties change at lower temperatures. This is because of morphotropic phase boundary. And at the materials with most high piezoelectric coefficient, 600, we observe nothing changes up to 250 Celsius. Thus, this material is good for high temperature applications. But what is more interesting is the properties, high temperature properties. These properties were measured directly at high temperature, and this is the dependence of strain on electric field at different temperature, unipolar field, and we can see that effective piezoelectric coefficient, which is measured at different fields, can be as high as 2500 at temperature as high as 250 Celsius. And if we compare with the existing materials, it is much higher than before. And the coercive field at this temperature is still high. We cannot measure it because we cannot obtain saturated hysteresis loops, but it is larger than 5 kilovolt per centimeter. This is good result for materials. And we can see that the properties are intrinsic. Thus, this is by the response force microscopy pictures measured directly at high temperatures for the MPB composition. And we can see that amplitude of piezoelectric response is increased at high temperature, 160 Celsius, as compared to low temperature, while the domain structure doesn't change noticeably. How we can explain this? We use the standard Landau-Ginzburg-Devonshire theory, Gibbs free energy is expanded as a function of polarization. And from the literature, we can estimate the coefficients. We took the same coefficients as for PZT ceramics because we don't know exactly from our material. And these coefficients were the same. And to obtain the agreement with our experiment, we need to change a little bit these two coefficients. And after that, taking the temperature dependence of coefficient before quadratic term, and with known Curie temperature and Curie constant, we obtain such kind of shape for potential energy at room temperature. We have the energy minimum in 111 direction, which corresponds rhombohedral symmetry as we measured by X-ray. And red ball shows the stable phase. Metastable phase is tetragonal. Energy is a little bit higher. And unstable phase cross shows the position of orthorhombic phase. And here the profiles of the potential in 111 in 001 direction. Tetragonal phase and metastable tetragonal phase and stable rhombohedral phase. What happens when we heat the material up to 200 Celsius? You can see that the energy of tetragonal phase becomes lower as comparison of rhombohedral, and we have very small energy barrier between these two phases. And when we look at these profiles, we can see that the barrier is small, and if we apply electric field along 001 direction, we can expect the field-induced phase transition from rhombohedral to tetragonal symmetry. And this phase transition is associated with the large, not only with the change of angle of spontaneous polarization. When we have change of angle, we have associated strain. This is known as field-induced rotation of spontaneous polarization. But also, we have field-induced extension of spontaneous polarization because the spontaneous polarization in tetragonal phase is much larger, and associated strain gives rise to very large piezoelectric effect. And when we remove field, the system goes back, and the energy barrier is small, and accordingly, the hysteresis is small. And then when we look at the picture at 350 Celsius, only tetragonal phase is stable, and the properties are much lower, but it is very high temperature, close to Curie temperature. And thus, our properties are because of field-induced transition from rhombohedral to tetragonal phase. Generally, this is known effect, and some papers were published quite long ago. This is the result for relaxer-based single crystals. We can see, again, here rhombohedral phase, here the transition from rhombohedral to tetragonal phase, and then tetragonal phase. Strain is large, but the problem is that it is highly nonlinear. Thus, it is not good for applications. Why we have linear or approximately linear relation in ceramics? It is because the field, the direction of field with respect to crystallographic directions are different in different ceramic grains. And this transition is become diffused in terms of energy, in terms of electric field. Thus, usually we know that properties of crystals are better than the properties of ceramics, but this is the rare example where ceramics works better than crystals. We have linear dependence. Thus, these are the brief review, the brief conclusions, and thank you for your attention.
All right. Any questions?
So sorry if you said this, but are these polled, these samples? Are they polled before you measure? Okay. So is there any dependence on the direction of polling?
No dependence on direction of polling. This is ceramics.
Right.
Thus, all directions are the same.
Okay. So you know that they're random grain orientations.
Yes, we have the picture of electron microscopy. It looks like usual ceramics.
A comment that might be relevant to understand the huge number that you get. A long time ago, we ran some simulations, first principles of bismuth scandate, lead titanate solid solutions, and we realized that bismuth scandate, if you solve it in the computer in the tetragonal phase of lead titanate, is super tetragonal. So bismuth scandate has a C/A of 1.3 or something like that. So I was wondering whether what you are calling tetragonal phase could actually be a super tetragonal phase, and so which gives you this huge strain, and therefore this very, very big value.
Sorry.
Yes, I suspect that what you have...
I want to give you a microphone because reverberation. Okay.
Okay. So the microphone doesn't... So I suspect that what you have as the tetragonal phase is a super tetragonal phase. Because bismuth scandate by itself, of course, you cannot synthesize it, but if you solve it in the computer with the usual lead titanate structure, happens to be super tetragonal with a C/A of 1.3. So I suspect
probably.
That 40% bismuth scandate is super tetragonal.
Yes, that's probably.
Because otherwise what you have would be what you would have in PCT when you go from rhombohedral to tetragonal, close to the photographic phase bundle. And there the number is not so large, right?
Yes. And it could be observed in different solid solutions.
No, but here you go to super tetragonal, and that's unique. Probably.
Yeah.
So, I believe an Indian group has reported about 1500 picometer per volt in bismuth ferrite doped with lanthanum and lead titanate ceramics. In about 2015, it's in Nature Materials. And then they see a kind of, I think, a disordered phase, disordered with some nanoscopic, at a nanoscopic level. And then which doesn't change much with the application of electric field. So it's a different explanation than MPB-related phase transition for how they get this high piezoelectric response.
And you mean
it's on ceramics.
By the post-force microscopy data, right?
Sorry?
You mean by the response force microscopy data, or?
No. It's just I think neutron diffraction and electron microscopy. So they report this intermediate phase, which acts as a bridge between moving from one polarization to a rhombohedral polarization, which eases it rather than an MPB kind of a formulation. Maybe we can discuss later. It's a Nature Materials paper. So,
see, of course, the intermediate phase can exist, but we can explain everything without any intermediate phase.
Okay, but structurally they see that to exist. So
probably, yeah.
All right, let's thank our speaker one more time. And everybody in this section.
Okay, I want to thank you. I want to thank all the speakers today and everybody. And the bar is open and the posters are up, and so everybody should be able to relax and talk with people at their posters. It's an important part of the meeting too, and I think there's enough refreshments out there to allow you to put off dinner a little bit.